we're going to try to finish up part 2 of our review for the final exam today. And let's see, I need to share the document. Here we go. And this could stand to be increased a little bit. Let's try. Give it about 25% increase. That's a little better. Now, let's see. I marked my place in red, I believe. Just need to find it.
I think it was like 138 or something like that.
Okay. $136. There it is.
Yes.
Okay. Let's see. There's one. Let me check for something. I want to be sure and get to one balancing equations. Let me see if I can spot it. I don't want to waste too much time, but I do want to get this one problem covered because it incorporates lots of things in one question. Well, there was one. We'll come back to that one. If I don't find it, then I'll just put it on the board because I've got it in hard copy here somewhere. Okay, let me go back. Here we go. All right, give me just a second. Okay, sorry for the interruption. Let's see. Okay, I'm going to do this one first because, let me see, my other computer will cooperate. Here it is. Okay. So we have this reaction given to you, and it's not balanced yet. Potassium iodide, that's written correctly, and nitric acid. Those two yield potassium nitrate. And oops, starting to give away the ending of the story. Nitrogen monoxide. Yeah, I'm going to run out of room. Let's see. I'm going to start over again. Not want to write this stuff down as we go because it's not in that document. There. Now, and iodine and water. Okay. So if you just take this equation and try to use the budgeting technique to balance it, you're likely going to fail. And the reason is a process called disproportionation, where you have an element on one side, in this case the reactant side, it ends up in two different places on the product side. That usually means that there's some redox going on. You've got some electron transfers in the process for that to happen. So the best approach for one like this is to balance the electrons first, and then use that preliminary or intermediate step of coefficients to proceed then with your budgeting scheme, right? So it's really a two-step process. So here's what we do. We have to find out where the redox is occurring. And since these are ionic compounds, except for that one and this one and that one, of course, these should be fairly easy to discern the oxidation states. So this one's going to be a +1 and a -1. That's easy. Alkali metal, halogen, there's no other choice. Hydrogens are always +1. Oxygens are usually 2 minuses. So that means we have 6 minuses there, balanced against a plus, which means 5 minuses. So now we only need 5 pluses to balance the rest of them. So that means this one is a 5+ oxidation state. I'll make myself a little more room up here. And the reason will be evident pretty quick. Okay, now on this side, you've got a plus here. This is a plus. So this one's going to be the same. 5+, 2-, right? So there was no oxidation reduction taking place here with those elements. This one didn't change. We haven't got to that one yet. But the nitrogen didn't change here. But over here, you've got 2 minuses. That makes this one a 2+. So we did get a change from here to here, but not from here to here. So the redox takes place from this source, from this reactant to that product. And while we're here, what is actually happening here? So we go here like this to there. For each nitrogen, the way it is now, you had to gain 3 electrons. 3 negatives, balance of 5+, gives you 2+ left over. So you gain 3 electrons. And that's per nitrogen. Okay? So remember what we said about redox. If you, the gain always equals the loss. So that's where we're headed. Initially, it won't be that way. So this one, remember, elements in their standard state are oxidation state 0. Okay. And this oxygen is 2-, and this one is 1+. So there's no change there in the oxygens, the hydrogens, the potassiums, only with the nitrogen and the iodine. The oxidation state on this iodine is -1, and over here it's 0. So it had to lose an electron. So here we have a loss of 1 electron per iodine. Okay, so now we have to balance So if we've got 1 electron here and 3 electrons there, the natural tendency is just to say, okay, we'll put a 3 in front of this one, but then you got three iodines here and 2 over there. So in order to make this work, we got to balance the iodines first, which would make it 2 here, and that would be 2 there. Okay, 2 iodines here, 2 iodines there. So 2 iodines per molecule. So now we've got to go from an even to an odd. And the best way to do that is to cross multiply. So we're going to say 2 here times this one and that one. Okay, so 2 times 3 is 6. And on this one, we're going to say 3. 3 times this. So 3 times that is 6. And that means we need there. Okay, so now we have 3 times this equals 6 electrons. Okay. This is your starting point for the standard budget. So you have a 6 here, 2 there, 1, 2, 3, and 1. And from that point, we can use our budgeting scheme. Okay. In order to make room for that, I'm going to have to erase some of this stuff. Okay. So I hope you've been writing it down. Well, it's being recorded, so there shouldn't be an issue. Okay, so now we've got our new starting place. There's a 6 here. There. Remember what we do. Since we've got nitrogen starting here in nitrate, ending there in nitrate, the temptation is to use nitrate as one of our components. But it splits. It's disproportionate. It goes from here to here and here to here. So we can't do that. We've got to do individual elements for every one. So we just start off with potassium, iodine, hydrogen, nitrogen, and oxygen. And then we set up our budget. On this side, we have 6 potassiums, we have 6 iodine, we have 2 hydrogens, we have 2 nitrogens, and we have 6 oxygens. Okay, it's our beginning position. Okay, on this side we have 1 potassium, right? We have iodine. We have 6 iodine. That's correct. Hydrogen. We have 2. That's it. 2 hydrogen. Excuse me just a second. And nitrogens. On this side we have 1, 2, 3. And oxygen we have 3, 4, 5, 6. Okay, so that's our starting point using our standard budget. We've already got the electrons balanced. So now anything we do to this equation, they're going to stay balanced. As long as we balance the number of atoms. All right, so where do we start next? Where do we go next? Let's see. I'm trying to think of the most efficient way. Well, we could do 6 potassiums here. But if we did 6 potassium, it would take that, be 6 here, and then that would increase our nitrogens. So 6, 7, 8. 8 nitrogens. Right? And 3 times 6 is 18, 19, 20, 21 oxygens. Okay? Now we got these two balanced. That one's balanced. How about the nitrogens on this side? So we need 8 nitrogens over here. And there's only one place that they're located, 8. Right? So what does that do to everything else? It doesn't change this one. 8 hydrogens. Right? Like that. 8 nitrogens and 24 oxygen. Okay? So now, where does hydrogen occur? Balanced, balanced, not balanced, balanced, not balanced. So we need hydrogens. We need 8 hydrogens on this side. And they only occur in one place. So we need 4 here, would be 8 hydrogens. And oxygens, now we count up 4, 5, 6. 6 and 18 is 24. So now you're balanced. You balanced both numbers of atoms and numbers of electrons. And this is sort of a hybrid approach. Whenever you see the potential for a redox reaction, it might be well to look at balancing the electrons first. Okay? So that one doesn't have a number, because for some reason it got left out of this document. Now we'll go back to the document. Okay, that's still centered. There we go. All right. So 142 is next on the agenda. And what we have here is a lot of blue smoke. It's a word problem, and they're notorious for giving you information that you don't need. But there's information that you do need, and sometimes there's information that's not there that you can find elsewhere. In this case, I think all the information is there. We just have to cut through the smoke. We'll give you a little background. Historical nitric acid was prepared 1,200 years ago by heating naturally occurring sodium nitrate, saltpeter, with sulfuric acid to produce sodium bisulfate, and collecting the vapors of HNO3 that were produced. Then you would just redissolve the vapors in water. Okay, calculate the delta H for this reaction. Okay, look at the information that's given. The balanced equation is given there for you. You can check it to see, right? There's some people showing up. I need to check to be sure I got you covered. Okay. Sorry for the interruption. You've got this equation that you want to see, be sure it's balanced. So you got the same number of sodiums. Nitrate is balanced. Hydrogens, you've got 2 hydrogens here, 1, 2 there. Sulfate on both sides. Okay, it's balanced. So look at the information that's given that's there to support the question. Calculate the heat, the standard heat of reaction for this equation. And all you're given is heats of formation. So what does that mean? That means that to answer the question, we need to use that formula for combining heats of formation in a given equation. We're given the heats of formation for all of the components. 1, 2, 3, 4, 1, 2, 3, 4. They're all there. So what's that equation? Delta H for that reaction is equal to the sum of the heats of formation for the products minus the heats of formation for the reactants. Okay? So now it's really simple. All you have to be sure to do is recognize that these values are given for 1 mole of the product. Remember we talked about that last time, how you write the heats of the equation for heats of formation. You start with the product, 1 mole of the product. And then the reactants have to be adjusted accordingly. So that heat of formation is only for 1 mole of the product. So you look at your equation and say, there's 1 mole there, 1 mole there, 1 mole there, 1 mole there. They made it simple. You don't have to multiply these by any values. They're all 1 unit. So you just take the product, this one, minus 1125.5. That's for one product, the sodium bisulfate, and the nitric acid right here, minus 135.1. And then you subtract sodium nitrate, saltpeter, minus 467.8. 467.8. That's a minus, but we're subtracting it because it's over here. And the other one, sulfuric acid, is here, minus 814. And 0.0. And that's a minus. Right? So that's going to give us a value. And since I don't have the answer key for this one handy, we'll have to calculate it. So we take 1125.5 and 135.1. Okay, that's minus 1260.6. And then we'll add, because this is minus, 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 we'll add 467.8 and 814. So that gives us a positive sign matters here, positive 21.2, okay, kilojoules. That's one thing I didn't check in advance, because for some reason, no, here it is, kilojoules per mole. Kilojoules per mole, that should have been expanded out here to the side of these. These guys got wrapped around. But they're all kilojoules. That's good. I should have checked that first to be sure they were all kilojoules, all same units, so we can add and subtract. Okay, so that means the answer is C. All right. So let me see here. I'll move down some. All right. And that equation should be in useful information. I'm positive it is. Okay. 145. The force between two bodies having identical electric charges. Okay, this is simple. You have to understand. You don't even have to know Coulomb's law. You just have to understand what happens when two charges approach one another. It depends on whether they're like charges or opposite charges. So in this case, they're identical electric charges. So we're expecting some repulsion. Right? Two negatives or two positives, doesn't matter. So let's see which one fits best. The force between them is a force of repulsion. Yes, that's true. Let's see how the others match up. B is a force of repulsion if the charges are negative, and one of attraction if they're positive. Okay, that's wrong. If they're like charges, they repel. So B is false. Increases as the bodies are moved further apart. No, it's not. As they move farther apart, the force, whatever it is, decreases. D is independent of the distance between them. That's false. It is dependent. It's just not dependent the way that C says it is. And the force is directly proportional to the distance between them. That's also false. Okay, this does require Coulomb's law to understand that part. So the force between the two charges is proportional to the two charges, how large they are. And there's a constant out here. I can't remember what it is. But it's inversely proportional to the distance between them squared. This is often referred to in not just this equation, but other equations as the inverse square law. The further away you get, the less is the impact of whatever you're measuring. But it's also not just less, but it's less by the square of the distance. Right? So that happens for gravitational effect, Newton's universal law of gravitation. Same thing, is the inverse square. So the only one that fits here is this simple statement of a force of repulsion. The rest of them are false. And that works for on the atomic level too. If you have a positive ion and a positive ion being brought together, they're going to repel each other. And the closer they get, the force goes up by the square of the distance, right? So it decreases as they separate, but it increases as they approach. Now, what does that have to do with compounds? Well, it has an effect on the whether or not, or at what distance actually, they tend to associate. So if you get two elements coming together, they're, well, actually, if they're both positive, they're not going to bond, right? But if you get a positive and a negative together, they're going to attract, like sodium and chlorine. But they attract only so far as the electrostatic effect is not overwhelmed by other forces. So let me explain. If we have sodium coming together with chlorine, they will approach one another because they're attracted. But when they get really close, and if you try to push them too close, right? Now what are they starting to feel? As they get closer, they feel the positive charge in the nucleus. So as the nuclei get closer, that's not right, those are neutrons. The protons. As the protons get closer, they're going to repel one another, right? So that attraction is only good up to a certain distance, and then they don't get any closer because they're now at a minimum energy. If you try to push more energy into the system, then you can get them a little closer, but they won't like it, and the repulsive force will be enormous the closer they get. Okay. Let's see, did I go? Yeah. Which of the following molecules has no dipole moment? All right. What are the two factors that are required to determine if a molecule has a dipole moment? First of all, what's a dipole moment? It's characteristic of a molecule in which the average distribution of electric charge, the electron density, is shifted toward one side of the molecule versus the other. If the electron density is the same all over, then you have no dipole. But if we shift the dipole slightly to one side of the molecule, then you get a dipole moment in that direction. This is toward the negative, that's toward the positive. So what's required to do that? Two things. One, you have to have polar bonds. You got to have one or more polar bonds in the molecule. Then you have to know the geometry. Because if you have polar bonds, but they're opposite one another, and they're forcing away or toward each other, then they cancel one another out, as long as they're equal in magnitude. Right? If they're facing each other, but one is stronger than the other, then you still have a dipole. But if they're equivalent, if these polar bonds are equivalent in magnitude and the same in opposite in direction, then they will cancel and you have a nonpolar molecule. Right? So you need to know those two factors to answer this question. All right, so 149 gives us these choices. E says none. Okay, so A is carbon dioxide. B is ammonia, and C is water, and D is all. Okay. So let's see which ones have dipole moment, if any. So what's the structure of CO2? You have to draw the Lewis dot structure and then use VSEPR, valence shell electron pair repulsion model, to determine the geometry. Right? So if we do that, in the interest of time, I already know what it is. So we're going to say this, that. Okay, that's the Lewis dot structure for carbon dioxide. It's linear. Now you do have a dipole this way and a dipole that way. They're equal and opposite. So this molecule is nonpolar. Okay. So that one satisfies. If these two are polar, then A is your answer. So let's see, what's ammonia? Well, draw the Lewis dot structure. It looks like this. Okay. That dipole moment is this way. So that one's polar. Water. It has a tetrahedral electronic structure, but a bent molecular structure. And the dipole moment is this way for that bond, this way for that bond, and overall is that way. So this one is also polar. That means that one can't be right, That one can't be right. A is the answer. Okay. This one is sort of tricky. Choose the molecule with the strongest bond. We have to consider two things here. One is the size of the atoms, because these are all halogens, right? So they're going to have a similar bond structure. In other words, p orbitals overlap to give these molecules. Yeah. And they're in order. They're in order in that family from top to bottom. So we could look at electronegativities and say that the electronegativities increase as you go up, right? So electronegativities would say something about their bonding potential. But what we're really looking at is if the p orbitals overlap, right, like that, and then we have another like that, and they overlap, they're forming similar bonds with their valence shells. The key here is that as the atoms get smaller, the molecules can move closer together. And remember, the shorter the bond, the closer the nuclei, the stronger the bond. Okay, so we should see the bonds increase in strength that direction, right? And that's true. This bond is stronger than that one. This bond is stronger than that one. You would expect this one to be stronger than that one. Except that as the molecules get closer, like we discussed in just a few seconds ago, the proton repulsion starts to take effect. And the fluorine is such a small molecule that if they get too close, the proteins repel. So the bond distance in this bond is, this one is shorter than that one. So actually the strongest bond is here. It's counterintuitive, but that's the evidence. And we try to explain reality. We don't invent reality in the sciences. So that's the explanation. As the atoms shrink, they can get closer together with the same type of bond until the nuclei start to interfere with that bond distance. So that's why fluorine is a longer bond and chlorine is a closer bond than either this one, or that one. Okay, I picked that one out because it was kind of strange and counterintuitive. Okay. Uh, 159. In the gaseous phase, which of the following diatomic molecules would be the most polar? Okay. In this case, notice that each one is ionic. So the attraction between them is going to depend entirely upon electronegativities. So you would expect that the most polar would be the one where the electronegativities are the farthest apart, the greatest distance. In fact, the greatest distance on the periodic table. So let's look, cesium fluoride. Cesium's way down here, lower left, fluoride is up there, upper right. That's a huge difference in electronegativities. So I'd say that's probably the case. That's probably the best answer, be the most polar. But let's see what else. Chlorine is less polar than fluorine. So that dipole is going to be less. How about sodium and chlorine? Well, sodium is way up here with chlorine. So it's less electronegative. I mean, it's more electronegative than cesium. So that bond is going to be weaker. Sodium fluoride is stronger than sodium chloride, but it's still weaker than cesium fluoride. And lithium fluoride, same argument. So the farthest apart they are, lower left to upper right, in this case is cesium and fluorine. And that's why A should be the answer to this one. It is the most polar in the gaseous phase. Why did we specify gaseous phase? Because in the gaseous phase, they're still molecular. They still bond. You can increase the temperature high enough to get them to separate into ions, but these molecules in the gaseous phase are still bound together, but we can't put them in the liquid phase, in aqueous solution, because then they separate into ions. And at that point, you can't talk about them as polar molecules anymore. So it has to be the gaseous phase. Okay, let's see. We did that one fairly recently, so you should be okay with this one if it appears. Any type like that appears on the test. You can draw the Lewis dot structure. You can use VSEPR to tell the geometry, the electronic geometry first, then you cover up the lone pairs and find out the molecular geometry. That's all there is to it here. It's simple. What most people left out in answering this question on the exam was they left a charge off. And the Lewis dot structure for ICl4 is different than ICl4 minus. So when you draw the Lewis dot structure, you've got to put the charge in, and you have to do it in brackets because the charge is characteristic of the entire molecule, not just one of the elements. Okay, let's see. How about this one? 176. Look at these molecules. They're cyclic molecules, and I've given the formula here to show you that each one of these, this is organic chemistry, so that's why I'm telling you right now that wherever two lines meet, like here, and there's no element given for the meeting, that's a carbon right there at that apex. So this one has 6 carbons, this one has 6 carbons, this one has 6 carbons. All of them have the same number of carbons, but we don't write the hydrogens either. We only write the hydrogen. You have to understand that for every carbon, you have 4 bonds. And for this carbon right here, there are only 3 bonds. So the other one is a hydrogen. So that means for each of these, only 3 bonds, each one has a hydrogen, right? So we would write it like might even put the carbons in. Okay? So follow that pattern. Over here, when you only have 2 lines coming in, there are 2 hydrogens there. And there are 2 hydrogens here. There are 2 hydrogens here, 2 there, 2 there, and 2 there. Okay, that's why the different numbers of hydrogens. Okay, now to the question. Which molecules have equivalent carbon-carbon bonds throughout the molecule? Okay? The issue here is to recognize the difference between a single double bond where you have a sigma bond and a pi bond together, that's what the double bond stands for, versus a single sigma bond. Now in this case, these sigma bonds here, there, and there, those are equivalent. But this double bonded one is shorter. So that tends to destabilize the molecule, actually, just as a side note. So you have different carbon-carbon bonds here. This one is a double bond, the rest are singles. These two are doubles, the rest are singles. These are double doubles, these are single singles. Now, the issue here is when you have these alternating double bonds, you get those lone p orbitals, right? So these p orbitals are unused. And what happens is you get an overlap of all of them. You get that smearing effect, which means that the bonds in C6H6 are all equivalent. Whereas the bonds in this one and this one are not. So the answer to this one should be 1. Just Roman numeral 1 has equivalent carbon-carbon bonds throughout the molecule. And that's based on evidence too. Experimental evidence says these are equal, these guys are not. That's why this one is so much more stable than the rest. This is benzene. Okay, just skip down to the next one. The electron configuration of this particular diatomic species is that given. What's the bond order? This is very simple. It's a simple calculation. Bond order for that molecule is what? The number of bonding electrons minus the number of anti-bonding electrons divided by 2. So let's look at it. How many bonding do we have? All right, look for the ones that don't have an asterisk. Those are bonding. So this one has 2, this one has 2, so that's 4 total, plus 4 is 8. So we have 8. Then we look at the anti-bonding. So this one has 2, this one has 2, so that's 4. Divided by 2 equals what? 2. The bond order of this molecule is 2. Answer is D. All right, that was really simple. Now, while we're here, let's take this one step further. Is this molecule paramagnetic or diamagnetic? Right? What does diamagnetic mean? Or what does paramagnetic mean? Paramagnetic responds to a magnetic field. Diamagnetic does not. Diamagnetic would be all the electrons are paired. Paramagnetic, all the electrons, or at least one of the electrons is unpaired. So let's see. How many can you have in a sigma? 2. Those have to be paired. Those have to be paired. Those have to be paired. Maximum 4 in a pi. So these are all paired. But the pi star has 2 orbitals in it, and we fill them one at a time. Spin up, spin up. That's all there is, 2 of them. So this molecule would be paramagnetic because it has those unpaired electrons in this anti-bonding orbital. Okay? Let's see. Dropping my utensils. Okay. Okay, we got about 15 minutes left, so let's see. Consider this molecule. What kind of hybridization for each of the carbons labeled? 1, 2, 3, 4, and 5 carbons are labeled. So what type of hybridization is it? All right. Yeah, let's draw it out. That's the first carbon. There's the second carbon. There's the third carbon. And it has that and this. And then we have the final carbon here, attached to nitrogen. Okay, something else about writing organic compounds. When we put a hydrogen right next to that carbon, that does not mean that the hydrogen is bound to this carbon here. That means this hydrogen is off here somewhere. It's a shorthand notation. This carbon is bound to that one, and it's bound to that one. This one's bound to that one is bound to this one, and those hydrogens are peripheral. Okay, now, what type of hybridization? Well, we know that if you have a triple bond, or if the molecule, no, if the molecule is linear, it's what? sp, right? So here we have that way, this is linear. So it's sp hybridization. This one is 1, 2, 3, 4. Right? Those two hydrogens are separate on either side. They would be like this and this. So 4 means sp3. This one has 1, 2, 3, 4 bonds, but it only has 3 electron groups. 1, 2, 3. This is sp2. This one has 1, 2, 3. It's also sp2. This one has 1. Did I write that correctly? Yeah. 1, 2, 3. This one's sp2. Right? So it's sp2, 2, 2, 3, and 1. So that would be A. There's sp2, 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 sp3, and sp. That means 180 is A. Okay? All right. Looks like I'm going to run out of time, so let me see what's next. All right. 204. You just have to know what the Heisenberg uncertainty principle is in order to answer this one. Let's see which one fits. It is impossible to accurately know both exact location and momentum of a particle. Actually, that's a pretty good definition. Let's see if any of the others get any closer. The exact position of an electron is always uncertain. Nope. You can sometimes know where it is, but you can't know its momentum, which is mass times velocity. And since the electron's mass is constant, you're really talking about the velocity. You can't tell how fast it's going if you know where it is. If you know how fast it's going, then you don't know where it is. Okay? And that's in terms of electrons. Right? And the Heisenberg uncertainty principle works for any particle of any size. C, the velocity of a particle can only be estimated. No, that's false. You can know it with pretty good accuracy. But if you do, you can't know where it is. The location and momentum of a macroscopic object are not known with certainty. Well, that's crazy, because the larger you get, the less effect the uncertainty principle has. Right? So it's really only significant. The Heisenberg uncertainty principle is only significant for very, very small particles. Even though it's true for larger masses like my body, the uncertainty is such a small component that I can know both my velocity and my position with reasonable accuracy. The location and momentum of a particle can be determined accurately, but not the identity. Okay. E represents the question maker's imagination. A, B, C, and D are reasonable perversions of the truth, but E is just completely ridiculous because we need 5 answers and we're stuck. So there you are. The best answer for this one is A. It's impossible to accurately know both the exact location and momentum of a particle. We probably should have said a subatomic particle or a very small particle. That would have been more accurate, but this is still the best answer for 204. How about Mendeleev? Remember him? He's given credit for the modern periodic table. And why is that? There are other people working in that arena. Mendeleev is given credit for one particular reason, although maybe not the only. But in the interest of time, I'll skip to the answer. He emphasized, C, he emphasized its usefulness in predicting the existence and properties of unknown elements. That's it. The predictive ability of the periodic table is what got Mendeleev recognized as its inventor. Okay. Nitrogen has 5 valence electrons. Is that true? Let's check our chart. Where's nitrogen? Okay, nitrogen's right here. How many valence electrons does it have? 1, 2, 3, 4, 5. 5 valence electrons. Which of the following electronic configurations represents the ground state for N minus? So if it has 5 ground states, when we add 1, now it has 6 electrons in its valence shell. Did I say 5? Not 5 ground state. 5 valence electrons, neutral atom. N minus means we have 6 electrons that have to be dealt with. Okay, so nitrogen does have a 1s orbital, but the valence shell we're talking about is the second period, right? So we only have to position 6 electrons, right? So we have 2s, right? And the 2s has to fill before the 2p. So that means A, D, and E are possible. Then we go to P. So how many do we have left? 2 from 6 is 4. We have to position 4 electrons in the p orbital. So we start off with 1, 2, 3, 4. Remember? Unpaired first, then we swing back and start pairing with the leftovers. So that means B would, no, not B, E would be the best answer because we have 2 here, and we have 4 here, which makes 6. Okay? Okay, we got another one. An element has the electron configuration of shorthand. Argon is the core. Then we have 4s2, 3d10, 4p2. All right, so how do you do that? To find out whether it's a non-metal, transition element, metal, lanthanide, or metalloid. All right. So you take your periodic table and you say argon. We start with argon right here. Then we're going to work our way. There's your 4s2 at potassium. 3d10 puts us all the way over here to zinc. And then 2 more electrons, gallium germanium. So the element is germanium. Is that a metal? Well, it's not a nonmetal, right? Because remember the zigzag, it goes like this. But it's right next to the line, the dividing line, which makes it, technically it's a metal. But anything close to that line in this region right here is a metalloid. So the best answer, a correct answer is C, but the best answer is E. It's a metalloid. Okay? In which group, 231, in which group do all the elements have the same number of valence electrons? Which one of these has the same number of valence electrons? They have to be in the same family because their chemical properties are influenced. They're not exact, but they're influenced by the number of valence electrons. And each group has the same number of valence electrons. So all we have to do is find out which of these has elements in the same family. So silver, cadmium, argon. Well, we know argon's a noble gas and these other guys are metals, so throw that one out. Sodium, calcium. Sodium's an alkaline metal, calcium's an alkaline earth. That can't be. This would be 1 and that would be 2 valence electrons. Doesn't work. Phosphorus, sulfur, chlorine. Chlorine's a halogen. Phosphorus and sulfur are not. So that's wrong. So the only one we got left is D or E. So it could be either D or it could be none of these. So let's say, where's phosphorus? Phosphorus is right here. And then arsenic is right under it. And selenium's to the right. Wrong family. So none of them are correct. Okay? And the answer is E. Okay, Mendeleev again. Which one of these is not a property that Mendeleev predicted? Oxide formula? Yes, he did that. Boiling point? Yes. Density? Yes. Atomic mass? Definitely. Electron configuration? No. They had no clue during Mendeleev's time about electronic configuration. That was complete. That was in the future. So A is the answer to 236. Let's see. What do we have here? Which of the following statements is always true concerning a reaction represented by the following balanced chemical equation? Okay, we're telling you it's a balanced equation, and we're saying which of the following statements is always true about this one? What type of reaction is this? Right? Well, we've got a hydrocarbon and an oxygen forms water and carbon dioxide. That is a combustion. Anytime you have oxygen reacting with an organic like this, it's a combustion. And all combustions are redox. Right, so we got those two going for us. Let's see which one. Okay, we're also introducing the concept of limiting reactant. All right, so we have to consider that. In fact, that's the focus. I was off on the wrong track. The focus is limiting, which is limiting. If we have equal masses of C2H6, which is ethane, and oxygen, there is no limiting reactant. That's false on its face. Why do we know that? Because the molar mass of C2H6 is much larger than oxygen. Okay, that means, well, let's see, can we say that? if we have equal masses, we're going to have to do a calculation. So what's the molar mass of C2H6? Molar mass is 12.01 times 2, and then 6 times 1.01. Okay. So 24.02 and 6.06. So it's 30.08 grams per mole. Okay. Oxygen, we know oxygen, it's 32 grams per mole. Okay. Now, they're roughly the same molar mass. I said the one was, actually, I lied, because the molar mass is greater for oxygen, but they're very close together. So we're going to use that approximation, that they're roughly equal, which means that the ratio of masses should be in the neighborhood of 7 or 6 to 2. Right? So it takes more mass by about 3 times more mass of oxygen to react with ethane. So if they're equal masses, yes, there is a limiting reactant. If we have an equal number of moles of C2H6 and O2, there's no limiting reactant. That's false too, because the mole ratio is not 1 to 1. The mole ratio is 2 to 7. So B is false. If we have more mass of C2H6 than we do O2, if we have more mass of C2H6, then O2 must be limiting. It doesn't say how much. If we have a little bit more mass, then no, if we have more mass of C2H6 than O2, that still doesn't give us an answer. If we have more mass of O2 than C2H6, then C2H6 must be limiting. Let's see what that means. If we have 2 moles of this, we're going to have 60 grams. If we have 7 moles of that, we're going to have about 220 grams. Okay, now we can say something about the mass. More mass of C2H6 than O2, then oxygen will be limiting. Okay, if we have more mass of this than that, then we're going to run out of this first. So with that logic, C is the answer. Did I confuse anybody? I almost confused myself. Okay. Which is the following is paired incorrectly? Weak and strong acids. What does it take to be a strong acid? Complete dissociation. Right, so H2SO4 is a strong acid based on the dissociation of the first hydrogen. Remember, the second hydrogen makes it a weak acid after the first one leaves. But the first hydrogen will completely dissociate, which makes it a strong acid. HNO3 is a strong acid that's incorrectly paired. And since there are no other possibilities, we don't have all of the 2 of the above, all of the above, none of the above. You can stop there. B is the answer. They're not paired correctly. Okay, we're out of time. So I think what I'll do is come back at 2 o'clock. I'll just leave this up here. And what I'll do is when this meeting ends, I'll get a video file. And when the lab time that we're going to have at 2 o'clock ends, I'll get a video from that one too, and I'll splice them together so that they'll all be in one package before I post them. But if you have to leave, then that's okay. I'll come back at 2 o'clock. And what we'll do first, at 2 o'clock, we'll field any lab questions first. And once the lab questions are satisfied with those who attend, then I'll jump into this document at this point and finish the discussion. Okay, so let's see. I'm going to stop the share. And that document should be held where it is. I don't remember where it is. Sure. Yeah, we're good. All right. So now we're at the point. We need to balance this equation. But the question requires that you don't just balance it. You recognize that it's a precipitation reaction. And that the question asks for 3 different versions. The balanced molecular equation is where you start. So that will be answering this question. Then you break it up into its ions, which is actually what's happening in solution. And that's the complete ionic equation, right? So then you'll look for the answer based on that one here. And then you remove ions that are the same on both sides of the equation, and that gives you the net ionic equation. Okay, but we're working from a word description, so this is why it's important that you know how to write compounds. So let's see, I'm going to pick a different color now. Let me see if black works. My brown's starting to get a little sketchy. We got aqueous solutions of barium chloride. This is, let's see, well, it's got 3 different numbers, so I'm just going to write this first. Barium chloride, aqueous solution. All right. So barium is an alkaline earth. Right? So that means it has a 2+ charge. Chlorine is a halogen and has a -1 charge. So in order to balance that compound, you have to have 2 chlorines. Okay? That's the first step. You got to write the compounds correctly. So that's a reaction with silver nitrate. Okay, aqueous. Is that correct? Nitrate's a polyatomic with a -1 charge. Silver has a +1 charge. You can look it up on your periodic table. It's one of those transition metals that only has 1 charge. It's +1. So those are the reactants. Now, what do they do? In this type of reaction, you have a double replacement. That is, the cations swap places. So the silver goes over here, and the barium goes over there. That's all you have to do to write the products. So we have barium nitrate. And this is a 2+ charge, and that's a 1-. So that means we need 2 of those. Now, is it aqueous? That's the question. You have to look in your look at the back of the document. Let's see, what page am I on? 69. So I can come back to the right page. This will be on the final. So there's your solubility chart. So let's see if we can turn our head sideways. Where's barium? Barium's right here. And then you follow it down until you reach nitrate. Well, it's the first one. Barium nitrate is a clear cell, so this is aqueous. It is soluble. Then we have to say silver with chlorine. Silver chloride. +1 charge silver, -1 charge chlorine. That's written correctly. But we need to know, is it soluble or is it precipitate? Is it a solid? So we look silver, which is, where is it? There it is, silver. And then follow it down to chlorine, which is right here. It's grayed out, that's a solid. So that's what precipitates in this reaction. Okay? Now we just have to balance it molecular wise. Let me go back up to 69. There it is. So this one's easy enough to do in your head. You got 2 chlorines here, and you got 1 chlorine there. So you need 2 here. Now you got 2 silvers, and you need 2 silvers here. Okay, let's check it. 1 barium, 1 barium. 2 nitrates, 2 nitrates. 2 chlorines, 2 chlorines, and 2 silvers. We're balanced. So this will answer question 266. So we look at the options. AgCl, S, right? To answer these questions, you have to take into account the coefficients as well, right? Because some of them have coefficients and some of them don't. So the best answer here is not just the compound, but how many of them are there? And B, in this case, gives you 2 AgCls. The reason this question is structured that way is so that we know that you've balanced the equation before you answer the question. Because if you don't balance the equation, then you can say, yeah, there's silver chloride there. I know that silver and that chlorine combined to make silver chloride, but I don't know how many there are because I didn't balance the equation. So you have to balance the equation to answer this question. There are 2 silver chlorides. They're not 2 barium nitrates. There's not 1 BaNO3 because you need 2 nitrates in that. So that's written wrong right there. And you don't have 3. So the best answer is B for this one. Now to answer the next one, we have to write the complete ionic equation. So how do you do that? Well, you take the ions. You know what the ions are because we had to know them in order to write the compounds. So you split them out. These are aqueous, so you have 1 barium with its charge. Now we're talking about ions, so the charge has to be there, but it's still aqueous. How many chlorides do you have? You have 2 chlorides. See, chloride is now not in the compound, so the subscript becomes a coefficient. You need 2 chlorides because you have 2 here. That's also aqueous. You have 2 silvers, aqueous, and 2 nitrates, aqueous. Let's see. There we go. And then I'm going to put the products over here. Barium nitrate. There's 1 barium. And there are 2 nitrates. What's left? Silver chloride. You can't change that one because it's a solid. It's not in solution anymore. The complete ionic equation leaves this as a solid. So you have 2 silver chloride solid. Okay. That's the complete ionic equation. And we look at our choices. 2 bariums? Nope, there's only 1. B, 1 chloride? Nope, there are 2. 2 silvers? Yes, there are 2 silvers there. Nitrates, there are 2 nitrates. That's not it. Silver chloride aqueous? Impossible. Silver chloride is solid. So the answer to that one is the 2 Ag pluses. C. Okay? Now for the last one, we just need to eliminate those species that occur on both sides in the same amounts. So barium here, product here. Okay. Nitrate here in the reactants, products, same. Okay. Now our chlorides are over here in a compound. We can't throw them out. Can't throw that one out either. So we have 2 Ag plus 2 Cl minus yields 2 AgCl solid. Now we normally write equations with the simplest whole number coefficients, right? So we would change this to 1, 1, and 1. Okay. So let's look at what's possible. We know we have silver ions, chloride ions, and silver chloride solid. So anything else we throw out. Throw out barium, throw out nitrate. Hydrogen wasn't there to start with. Silver chloride aqueous is wrong. So the best answer is 2 silver ions. Right? And that's the way it was before we reduced it. Right? So in this case, you're looking for the best answer. And since none of the others work, 2 silver ions in aqueous solution is the best answer, A. All right. That's erasing pretty good. Okay. Let's see. Let's track down a little bit. See what I got marked out next. Okay. 279. You're holding 2 balloons, an orange balloon and a blue balloon. The orange balloon is filled with neon. Blue balloon is filled with argon. The orange balloon has twice the volume of the blue. Okay, now I can draw my picture. Because the orange balloon is first with neon, and it's twice the argon. So that's neon, and then argon. This is what color? Orange. And blue. Okay? Twice the volume. So V neon versus V argon means that this one is twice the volume of that one. Okay? Which of the following best represents the mass ratio of neon to argon? Let's see, we want mass. Mass. Okay. What do we know, according to Avogadro, if this volume is half that volume, or this one's twice that volume, the number of moles here is equal to twice the number of moles of argon. Okay, all of the things being equal, pressure, temperature, if they're the same, then these two volumes are related the same way with volume and with moles. So now we know that we have twice as many moles here as we do here. So how do we relate the masses? You need to know the molar mass of each one. So the molar mass of neon is about 20. And the molar mass of argon is about 40. Okay. So what's the molar mass? The molar mass is mass per mole. So it's 20 grams per mole of neon. And this one is 40 grams per mole of argon. All right. So you've got twice as many molecules or twice as many atoms over here that weigh half as much. So the ratio should be 1-to-1 for mass, right? Let's just pick a number. Say you have 1 mole. 1 mole here. That means you have 2 moles here, right? So 2 moles times this would be 40 grams. And 1 mole times this would be 40 grams. They're equal in mass. So the ratio is 1-to-1. Okay, let's see what we have here. Oh, calorimetry problem. All right. That's 283. Okay. So let's see, what's the question here? Which metal was used? All right, so we're going to pick out the metal. You have to pick out the metal based upon its specific heat, right? So we have to determine the specific heat of the metal in this experiment. All right, so what do we know about calorimetry? If we're using a calorimeter, then we know that we have an isolated system. It's not an open, it's not a closed, it's isolated. That means energy can't cross the barrier, matter can't cross the barrier. So everything that we put in Vegas stays in Vegas, in the calorimeter. That means that everything that happens in there relative to heat has to be equal to 0. We can't create or destroy energy. And since there's none coming in and going out, then whatever's in there stays there. So that means the total has to be equal to 0. So let's see what we're told. 45.9 grams of the metal is heated. So the metal mass, let's see, let's put it up here. The mass of the metal, let's see, the mass of the metal is 45.9 grams. All right. We're going to put it in water that has 120 grams. So the mass of the water is 120 grams. Those two go together in the calorimeter. But the initial temperature of the metal is 95.2 degrees. So the temperature initial of the metal is 95.42 degrees C. What's the initial temperature of the water? The initial temperature of the water is 21.6 degrees centigrade. Okay. Now, what else are we given? The specific heat of the water is 4.18 joules per gram degree centigrade. And that little C is an archaic version. It's an older version of the specific heat. Now we use a little s. So the specific heat of water is 4.18 for this problem, joules per gram degree C. Okay. What we don't know, that's water. What we don't know is the specific heat for the metal. That's the question. Because in order to find out what the metal is, we need to judge based on the specific heat. Okay, the final temperature is 24.5 degrees. Now, why did I do it that way? Because when they come to equilibrium, they're both at the same final temperature. Okay? Let's see. All right. One thing that's assumed here that we are not told is the contribution of the calorimeter. So we have to assume that the calorimeter is ignored. In reality, if we did this experiment in the lab, we would have to determine the calorimeter constant and take that into account. But for this problem, we can ignore the calorimeter. So what's the formula that we operate under? The heat of the metal, which is equal to the specific heat of the metal times the mass of the metal times the change in temperature, final minus initial. So final is 24.5 minus initial is 95.2 degrees C. Okay, and we add to that the change in heat for the water. So this is the Q for the metal, this is the Q for the water. So over here we're going to have 4.18. I'm going to leave the units out just to save room. And then the mass is 120 grams. And then the change in temperature is final minus initial. Here we go. That's the thinking part. The problem is set up. Now all we have to do is solve for this value right here. And I don't remember what it was. I guess we can go ahead and do it. So let me get my calculator out. All right, what's the change in temperature here? It's going to be a negative number, 24.5, and then minus 95.2 is 70.7. I'll just write that. Minus 70.7. Okay, times 45.9, which is minus 3245. 3245. Yep. Minus 3425. And that's times its specific heat. Right? So this is going to be grams degrees centigrade, units for that one, grams degrees centigrade. Then we add what this one is. We can do that whole thing. 24.5 was the final, minus the initial 21.6 is 2.9 times 120 times 4.18. And that's 1454. 1455 rounded off. And this is joules. Okay? So now what do we do? Well, we erase because I run out of room. I need some space. Okay, so now we have this one right here. So if we take that whole number, now we have to resolve for an unknown. And this is algebra. You put this term here on the other side. Now it becomes negative. Negative 1455 joules equals specific heat of the metal times minus 3425 gram degree centigrade. Okay. Now to solve for this one, you divide both sides by that number. So it gets rid of it here, puts it over here. Okay, now we just have to resolve those two terms. Let's see. There. And I get 0.45 joules per gram degree C. It's always good to keep the units when you can, if you're not running out of space. Joules, gram degree centigrade, those are the units of specific heat. So we know, at least we did something right. So let's see, is that available? 0.45. It looks like it's iron, B. Okay. That's our calorimetry problem for today. I have to use a light touch or my board will flip over. The poor cat. Okay. 285. For this one, for which of the following transitions does the light emitted have the longest wavelength? Okay. 285. So what does longest wavelength mean? Well, in this context, when you're talking about electronic transitions, you're talking about energy. So the energy required for those transitions for an emission, what do you need to have an emission? You need an electron to move to a lower level, because lower means closer to the nucleus is lower energy, and that means now you give up energy, right? It's formula for energy in the form of light. So we're going from a higher N value to a lower N value. Let's see if that's true. Let's see, 4 to 1, 3 to 2, 2 to 1, 4 to 3, 4 to 2. Okay, those are all possibilities because they go from a higher number to a lower number. Next, longest wavelength implies what? The smaller the jump, the lower the energy. The longer the wavelength, the lower the energy. Remember, long wavelength means smaller frequency, and smaller frequency means lower energy. So small frequency, long wavelength is what we're looking for. the narrowest jump from one level to the other. Okay, let me redraw this. In level 1 is here. In level 2 is out here. In level 3 is a little closer, and 4 is even closer than that. So the farther out you get, the distance between the energy levels is narrower. So if we were to start from here and go all the way to here, that'd be a huge jump. That would be a short wavelength. All right, do we have any of those? Yeah, 4 to 1, that one's too long. Now 3 to 2 is possible from here to here. That's B. All right. And 2 to 1 is here. That's C. Right. So that's more energy than B. B is better than C. We already discounted 4 to 1. That was A. Right. So A and C lose to B. B's still our best answer so far. 4 to 3. Okay, 4 to 3 is D. All right. D's our winner at this point because it's the lowest energy. How about 4 to 2? Nope. D gives us the least amount of energy emitted by that jump. Excuse me, I got to kill a cat. Yeah. Oh, she got away. So D is our best answer. It's the narrowest jump of the electron, gives us the lowest energy, longest wavelength. Okay, 287. (287) tests your knowledge of orbital quantum numbers for orbits. So for 287, we've got these possibilities, and we want to find the incorrect one. 6s3p, 1p, and 4f. Okay, principal quantum numbers are these first ones, right? Those are the n's. So n is 1, 6, 3, 1, 4. The next one is the L value. Remember that one? The angular momentum quantum number. This implies direction. And for the L numbers, they are always possibilities, are the same numbers of possibilities as n, but they start with one less. So for 1, the only possibility is 0. For 6, you could have 0, 1, 2, 3, 4, 5. Okay. For 3, you can have 0, 1, and 2. For 1, you can only have 0. And for 4, you can have 0, 1, 2, and 3. This is S. 1 is P. 2 is D. And 3 is F. Okay? That's what they mean. Those numbers are given these letter designations. So let's see, is this possible? 1s. Yep, That's true. 6s. 6. There's an S right there. That one's true. 3D. Okay, 3. SPD. That's true. Okay. 1p. Now that's S. There's no P for 1. So that's false. And 4F. 4, there's your F. That's true. So D is the wrong one. 1p is not allowed in the quantum mechanical atom. All right. We're going to jump back to some Lewis dot structures with 299. Okay, in the molecule Xenon Difluoride, how many pairs of electrons surround xenon? And what is the molecular geometry? Okay, so in order to answer this question, and the answer is in 2 parts, we have to know the Lewis dot structure to begin with. So xenon difluoride. Okay, Lewis dot structure. How many valence electrons are there? Xenon is a noble gas. There are 8. Fluorine is a halogen, so it has 7 each, which means 14, which means 22 electrons in the valence shells. Now we distribute them with xenon in the middle. We use 2 4 electrons. 2 4. Now we have to place the other 18. Fluorine still has room for 6 more because you got 2 here. You need 6 more to make an octet. So there, 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 there. All right. 2, 4, 6, 8, 10, 12. So that's what, 6 electrons? Now, the only place those 6 electrons can go is on xenon. So we got 1, 2, 3 pairs of electrons. Is that right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Apparently that's right. 7, 3 pair. Okay. So apparently there's no right answer here. How did I get 4 pair, 5 pair, 6 pair? Unless 2, 4, 6, 8, 10. 1, 2, 3, 4, 5. Maybe that's it. There's a pair here in that bond. There's a pair here in that bond. Right. It does not say lone pairs. It says how many pairs of electrons. All right. So the reason that it's saying that is once you know the number of pairs of electrons, electron groups, 1, 2, 3, 4, 5, then you can say something about its structure. Right? So if you have 5, what is the electronic structure here? It's trigonal bipyramid. Okay, that means you've got, let's see, like this, like this, like this, and then you've got xenon in the middle, fluorine up there, fluorine down there. And your pairs here, 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 here. Now, why did we put those lone pair electrons here? Because that separates them maximally from each other. If we had put one down here, then that would make it 90 degrees from another one, but the other two would be 60. This is both balance and maximum distance. And it gives them more room to balloon out. Remember, lone pairs balloon. So this gives them more room to balloon. That way, the molecular structure here is linear. So 5 pairs of electrons, 5 groups, with a linear structure, which makes it the answer C. All right. Let's see. What do we got next? All right. Consider the following data. Use Hess's law to find the change in enthalpy. Okay. This one's going to take some work. Remember Hess's law. Hess's law says that based upon the fact that enthalpy is a state function, in that case, it doesn't matter how you get from a reactant to product. The delta H is the same no matter what the route, because enthalpy is a heat potential. So that means that we can write any number of valid equations into a summation to get the target equation. And that's what these are used for, to give you that target. Right? I'm probably going to run out of space, but I'm going to try to squeeze it in here. So what's our target? Calcium carbide. Oh, that needs to be subscripted. There we go. Calcium carbide. Let's see, how about the rest of them? Let me look for any anomalies here. No, they're all good. Okay, calcium carbide. And we need to write the state, because the state's important when you're doing a Hess's law manipulation. Calcium carbide, 2 waters, liquid, yield calcium hydroxide, plus C2H2. That's acetylene gas. I've mentioned that one before. That's what this is the reaction that allowed coal miners to go underground with their little lamps. They put calcium carbide crystals in there and pour some water in it. It would make acetylene gas, and then they just flick a lighter and turn on the light. You know, until they hit a pocket of methane inside the mine, and then, or coal dust mixed with air in the right proportion, and then the whole thing would go up. But we want to write this in terms of Hess's law. All right, so calcium carbide. And the determination in here is to find out the enthalpy change, right? The delta H. So let's find one for calcium carbide. Where's calcium carbide? There's calcium carbide. And are there any others? No, there's calcium carbide. Okay, first thing to notice is that calcium carbide in this equation is on the wrong side. It's a product. We need it as a reactant. So what happens to the delta H when you make it a reactant? You flip the equation, and the sign on delta H changes. So we're going to write it backwards. Calcium carbide yields calcium solid plus 2 carbons. And that's graphite. And the enthalpy for that is plus 62.8. Kilojoules. Okay, so we got this one. That one's done. Now, what's next? Water. Okay, so let's see. Which one has water in it? Well, we got this one with water in it, and we got that one with water in it. So which one do you use? Let's take the first one. Yeah, take the first one. So water it's on the correct side, but there's not enough of it. We need 2 moles of water. All right? So we've got to double that equation, and the delta H then is the same sign, but it's twice as much. So 653.1 twice that is 1306.2. And then we write the equation correctly. 2 calcium oxides plus 2 waters yields calcium hydroxide. 2 of those also. Calcium hydroxide. Okay? So we've used the first equation and the second equation. And we've got that one covered. Okay? Now, now we've got too many calcium hydroxides. Okay. I may have done the wrong one first. Yep. Okay, hold that thought. Let's go to the next one with water in it, which has acetylene on this side. We flip that equation. That gives us 1 acetylene and 1 water. So we're going to put acetylene and oxygen on the product side and carbon dioxide and water on the reactant side. And we're not going to change the numbers. We're just going to change the sign. So it's 1300. And then we put acetylene on this side. Let's see. Oh, no, I'm sorry. Acetylene goes on the other side. We need carbon dioxide and water on this side. You know what? I can see where this is going. Let's take that one back down to 1. And that takes this one back down to 653.1. There we go. And then we have acetylene on this side. And oxygen. Okay. Oxygen gas, yes. Okay. Now, these 2 waters take care of that water. This one is covered now, here. And now we need calcium hydroxide. Calcium hydroxide, we skipped it somewhere. No, wait a minute. There it is, calcium hydroxide. Okay. So we only needed 3 of those. We didn't need all of them. Let's be sure. All right. Okay. Calcium carbide here. Waters. Calcium hydroxide here. And acetylene here. Those are the only ones that we need out of those combinations. So that means that the rest of them must cancel. So calcium is here. There's no calcium there. So what we've got to do is take this one. We skipped the second one. And we've got to get rid of calcium. Calcium's a product here, so it needs to be a reactant, and it is a reactant in that scenario. So we write it as is and carry this number as is. We only need 1 calcium. So calcium solid plus oxygen gas yields calcium oxide solid. And that heat is minus 635.5. Okay. Now, this calcium is gone. Carbon. Where's the carbon? We don't have a carbon in there. That's the last one. So carbon's a product here. It needs to be a reactant here, but we need 2 of them. So carbon graphite, in this case, is the right side of the reaction, but the wrong amount. We need 2 of them. Plus oxygen. That's 2 oxygens and 2 carbon dioxides. Oops. Let me write that a little better. Two oxygens and 2 carbon dioxides. And we have to double 393.51. $787.02. Okay. So now, where were we? Carbon. 2 carbons. 2 carbons. Come down here. Calcium oxide. There and there. All right, see, here's our dividing line right here. Products, reactants. Water's covered, water's covered. That one's covered, that one's covered. Carbon dioxide, 2 here, 2 there. Opposite sides. Oxygen. Ooh. Calcium and oxygen. Graphite and oxygen. That leaves us 3 oxygens. Oh, here it is. There's an oxygen. Carbon dioxide, water. Yeah. So this one cancels this one. But we still have 2 oxygens left over. I'm missing oxygen somewhere because it's not supposed to be here. Let's see if I wrote these correctly. Let's see. The first one is calcium graphite, calcium carbide. Here. That's it. Calcium oxygen, calcium oxide. there. Calcium oxide in water is calcium hydroxide. That one's right. Acetylene and oxygen is 2 CO2s. Acetylene and oxygen is 2 CO2s and water. I wonder if that's written correctly. No, that equation is not balanced right there. Notice we've got 2 carbons here, 2 carbons there, correct. 2 hydrogens, 2 hydrogens, 2 oxygens, 5 oxygens here. So that equation is not written correctly right there. What should it be? All right, we got to fix acetylene plus oxygen, C2H2 plus oxygen yields CO2 plus water. All right. Well, let's put the coefficients as they are now. That'll get us there closer. So we have 2 here. Okay. How many carbons do we have on this side? 2 and 2. Carbon, hydrogen, oxygen. 2 carbons. 2 carbons. Hydrogens. 2 hydrogens. 2 hydrogens. 2 oxygens. 4, 5 oxygens. All right. So how do we get 5 oxygens over here? We use our fraction. 5 halves. And that gives us 5. Okay. Normally, we would go for reducing the fractions to whole numbers. But in this case, it's going to work better for us if we just use that fraction. So there should be a 5 halves here in front of that one. There we go. That fixes that equation. Now we need to take that back to our original. All right, so which one was it? Acetylene and oxygen, CO2 and water. Here, this should be 5 halves. Right. And plus 1300 is fine. Okay, now let's see if we can cancel things out. We've got 4 oxygens here, 5 oxygens there. No, wait a minute. We have 5 oxygens total. We have 1, 2, 3, 4. Actually, we've got 6. We got 6 oxygens here. This is not working. All right. Here's what I'm going to do. Rather than waste a bunch of time on this one, because it's obviously screwed up, I won't put this one on the final, and I'll check it before to be sure. I'm pretty sure this one would be a extra credit anyway, because it takes so long to work, and I generally don't give basis questions that take this long to work. But it needs to be fixed. And if it can't be easily fixed, I'll throw it out. No use keeping this one in the question bank if it's completely bogus. So let's look at some others that make difference. Okay, we've done this one recently. These molecules where you have this information. So I'm not going to spend any time on this one. All you have to do is go back and look at the test. This was a test question, so you'll find it in one of your exams. Just go back and look at it. And there. Now let's see. I think I had one other one that I wanted to do that's not included in this group. Let me clean this up. All right. Okay. So I've got a problem. The one thing that we haven't covered yet, reviewed actually, is the empirical formula, molecular formula from analysis data. Okay. So I'm going to do one of those right now. Okay. Here's the thing. I'm going to leave out the fluff. The compound contains only carbon, hydrogen, and oxygen. Okay, those three elements. And here's the analytical data for the compound. We have 2.78 grams is the total mass. Yeah, 2.78 grams is the total. All right. The analytical data says that the when it was combusted in oxygen. All right, so that's not right. Give me the raw data first. This is the compound. When we combust it in oxygen, we collect 6.32 grams of CO2. Okay, and 2.58 grams of water. Oops. Okay, that accounts for carbon and hydrogen, but we don't have an independent determination for oxygen because oxygen was used to combust the sample, right? So you can't determine the oxygen except by difference. If you know that it's carbon, hydrogen, and oxygen only in the compound, then once you find out how much carbon it is, how much hydrogen it is, then you subtract those two from the total and you get the oxygen, right? So we need, how much carbon does that represent? Okay, so we need a conversion factor. If this is CO2 and this is water, then we need a conversion factor for each that takes grams of CO2 versus grams of carbon. And this one is grams of water versus grams of hydrogen. Okay, so that tells me that we need composition of the elements. So how do you get the amount of carbon in carbon dioxide? Well, in one molecule or in 1 mole of carbon dioxide, carbon would be 1 carbon, 12.01 grams. But the total mass of carbon dioxide in grams is what? Is 12.01 plus 32. Right? So it's 44.01. Okay? So that gives us 1.72 grams of carbon from this compound. How about hydrogen? Well, hydrogen is 1.01. Actually, it's 2.02. Why? Because we got two of them. 1.01 times 2. What's the total? 2.02 plus 16, or 18.02. Times this, cancels that, cancels this, and gives us hydrogen, which is 0.29 grams. 0.29 grams of hydrogen. Okay, so how much oxygen is there? Oxygen then equals 2.78 minus 1.72 minus 0.28. And that should be 0.77 of oxygen. Now we have the composition of the element. Okay. This is not given in percent, so we don't have to use that trick where you say 100 grams for percent. We do have mass, so we can convert these directly into moles, right? Because if you want to know the empirical formula or the molecular formula, you have to know the mole ratio, not the mass ratio. Moles. So we convert these into moles of each. Okay, I'm going to have to erase this because I've run out of room. All right, so 1.72 grams of carbon is how many moles? Grams per mole. 12.01 per mole. Hydrogen, 0.29 grams of hydrogen. I think that's right. Yeah. Now we need a conversion factor for hydrogen. 1.01 grams per 1 mole. And oxygen. Ooh, I erased something here. 77. There we go. Oxygen is 0.77 grams. And we need a conversion factor for that one, which is 16. Okay. Now, do the math, and you get 0.143 moles of carbon, and we get 287 moles of hydrogen, and we get 0.048 moles of oxygen. Okay? Now I can erase this. Okay, so this is the mole ratio of each one of these elements. But it's not the whole number mole ratio. So what we need to do is divide by the smallest number to start with. So we divide each by this one. That's 1. This one is 6. And this one is 3. Okay? So now, which one is this? The empirical or the molecular? This is the empirical ratio, right? So this is going to be C3H6O. Okay, that's the empirical formula. Now, to find the molecular formula, we need to locate our multiplier. There. What's that X? Well, we need another piece of information. We need to know what is the molar mass of the molecule, of the compound. And we're given a range between 100 and 150. So the molar mass is between 100 and 150 grams per mole. Now, how's that going to help us? Well, you may surprise yourself. How do we get that value right there? We find out what's the empirical weight, the empirical mass, and compare it to this one in whole number increments. Right? So this one is going to be 3 times 12.01, 6 times 1.01, and 16. Right? 1 times 16. So that value is 58.09. Now all we have to do is compare this number to that one. That one? Nope. So that's not the molecular formula, because this would be 1 in that case. What if it's 2? What's 2 times that? Well, let's see. That's 1/8. That's 16 and 116.18. Right? So that does fall between these two. What if we do 3 times, just to be sure? So 3 times that would be 7. This is times 1. This is times 2. This is times 3. 17, 2, 14, 1 and 6 is 7. 174 is too much, right? It's outside the range. So this is the only possibility where X is equal to 2. So that means it's C6H12O2. Okay? So that's your answer. Let's see. I think that's all I had identified. So you can take a look at the video when I get it posted, and study your old exams. Look for those problems where you missed a question and you don't remember why you missed it. You could not go in and work it now. Those that you missed and you're confident you can go in and work that problem now, you know what your mistake was, you fixed it. Don't spend a lot of time on those. Just on the ones that where you missed it and now you can't remember why you missed it or how to fix it. Those are the ones you need to focus on. Okay. That was an hour and a half. Let's see. There's another half hour if you have any other questions. Or I can stick around for a little while in case somebody else shows up. But I'm done with the review. You know, unless there are specific questions, then I'll be happy to tackle them with you.